Hello, everyone. So this will be the last set of lecture slides we'll have, and then next week we'll do a review. Okay. All right. So chapter 11, part 3, intermolecular forces summary and solutions. All right. So here's a summary of the intermolecular forces we have looked at and some examples. For example, propyl alcohol has dipole-dipole, has all the forces, and same with acetic acid. Diethyl ether has everything except for hydrogen bonding. Ethyl fluoride has everything except for hydrogen bonding. And then tin tetrachloride has everything except has only dispersion forces, and because it's nonpolar. Okay, so I will post more examples for practice, but be able to differentiate the types of forces present in each molecule, and to draw some diagrams of them. So here are some examples of the boiling points of three classes of compounds, and you see here that as we go down the period here, the more mass increases, and with that we see a trend of increasing intermolecular forces, and with that increasing boiling point. And then we see that the difference between alkanes, nonpolar, so let me write that down. So alkanes, nonpolar. And most polar. We see a trend where the more polar we get, the higher the boiling point we get. And we see carboxylic acids. They have hydrogen bonding, so they have the highest boiling point. Okay, so those are some more trends to think about in terms of molecular weights. The higher the boiling point, the higher the molecular weight. Okay, so that's the trend. Okay, so here's the relative strengths of intermolecular forces. So dipole-dipole around 5 kcals per mole. Dipole-induced around 2 kcals. Induced dipole, the induced dipole around 5 kcals per mole. Ironically, that one seems a little bit stronger than dipole-induced dipole. Not sure why that is. And we see hydrogen bonding, the most particularly strong one. 4 times as strong as a typical dipole-dipole. Then we have an ion dipole force. This is usually what we see for an ion interacting with water molecules. So that's a really strong force. It's almost equivalent to a bond, almost. See the covalent bond, 243. It's stronger than a covalent bond, so that's pretty impressive. And then ionic bonds are the strongest, metallic bonds are the weakest of the typical bond types here. And we see those different types right on display, so different examples here. So be able to know and identify all these different types. I wouldn't worry about too much about the bonds, but ion dipole definitely is something we should think about. Okay. All right, so in a solution, usually we talk about a phase diagram, and basically a phase diagram tells us the combination of temperature and pressure that gives us the state of matter. So if you ever worked with like a vacuum, you might have noticed that the boiling point can be decreased if we decrease the vacuum. For one good example of this is if you ever cooked in high elevation, like in Colorado, you would notice that it may take less time to actually boil water. And that's because the temperature of water, the boiling point decreases at higher elevation where pressure is lower. So that's one way to take advantage of cooking. And there's all sorts of types of cooking, food, certain packaging that says, cook this at higher elevation. So there's definitely a lot of things to consider for kind of taking advantage of the properties of how we view water. Okay, so if you look at this curve here, if we decrease the pressure low enough, okay. Let's see here. So the boiling point, let's see. Okay. So right. So if we move left through the curve, we see here that if we move this way, we can actually lower the boiling point, because if we follow this curve here, it's going to move further to the left. And that will actually decrease the boiling point at a decrease in pressure. So if we follow this line as it decreases away from the dotted line, we can actually get a lower boiling point, and that's what happens at higher elevations, okay? All right, so this is a typical curve for water: solid, liquid, gas, and this point at the center. So the point where the three curves meet, that's called the triple point of water, and then that's basically an equilibrium where all three states can exist at once. And there's some interesting experiments with this, but I won't go into it. And then you reach a point where I don't think it says it here, but it may say in the other diagram I have. But you also get to the critical point of water, where it's a pressure and temperature combination where you can't differentiate the difference between the liquid and salt gaseous states, and that happens at certain conditions. Okay. And then the supercritical region, I believe is that if you're going towards part C, that's where you get to the yeah, I'm pretty sure past that region, or past, going towards the C, there is where you get to a point where it can no longer differentiate between a liquid and a gas. But don't worry too much about that, okay? So yeah, the critical point is it's part C. It's right. Well, it's pretty much this area over here, where you now can't really differentiate, or it becomes a supercritical fluid right there. So here's a more of an example right here. Oh, sorry, this is supposed to be for this diagram. See right here. So here's the triple point, and here are the vapor changes here, and then the supercritical fluid is where you that area past the critical point, where you can clearly identify liquid between liquid. The fluid is a liquid or a gas. Okay. So I might ask some questions about, like, I'll show an example in this next slide here. Okay, right here. So say these are my diagrams, right? So here's two phase diagrams of water. We have a linear temperature axis, and then we have here, this is just to show a kind of a region of the ice and water, a zoomed in region. Okay, so I might ask questions like, predict the physical form of a sample of water at 400 C and 150 ATM. So you would go to this graph. So we would go 400 C, so here's 400. Okay, and then we'll go all the way up to 150, and we see here that's point A, right? That's point A. 150 is point A. So in this case, our sample will be a gas. So this is in the region of water vapor, right? So that's the gas. So we can say it's a gas. Okay, so that's all you pretty much have to do. Is trying to pinpoint the axis and see where the state is. So that's a gas. So pretty straightforward there. All right, so now let's describe the changes that occur as a sample in part A is slowly allowed to cool to -50 degrees at a constant pressure of 150. Okay. Okay. So at 400 degrees, as we go from A to B, right, we're going to go to we're going to convert from a water vapor. So from A to B, we go from A to B, right? We're going to cool and we're going to condense. Condense to a liquid, okay? So we're going to condense to a liquid in this, if we're going from A to C, right? If we're going looking from A to B, sorry, okay? So in this case, we will have a combination of liquid and vapor water, liquid and vapor. Okay. So we go from A to B, that gives us, we're now going to condense to a liquid, and then from B to C, it's going to be mostly liquid water. So we're going to go from to the boundary to liquid water. And then when we go to C to D on our curve in point, so the curve I'm looking at is in part A right here. So in part A. Okay. So we go from B to C to D now. We're going to go to melt. Sorry, not melt. We're going to cool to solid water. So now at this boundary we have liquid plus solid H2O, right? Okay. And then we get to the point we're from C to D. We're going to now go to C to D. We're going to cool the solid water. So now we're at this point, at point D, right? We have now a combination of liquid and solid between those 2 points. And then when we go from D to E, liquid, water freezes, and we have solid water. And we have now, at the end of the day, we have solid ice that forms as the last thing that happens to our sample. Okay? All right. Now let's look at a different a phase diagram. Here's the phase diagram for carbon dioxide. So you see here the really big difference of carbon dioxide if we compare these two graphs, right? You see that the gas state is kind of curved up a bit, and it's usually a bit peculiar in the sense that the the curve is kind of skewed in the opposite direction, right? So it's kind of skewed in the opposite direction a little bit, but not by much. So the thing to note is that since we have a less polar molecule, we're going to have less, the boiling point and melting point are going to be different, but most interesting, the critical point is very you can actually reach it at certain temperatures and pressures. So whereas the critical point for water, if we look up here, the critical point is past the boiling point. If you look at the critical point, right? The critical point is actually, it's around 30 degrees C. So we can actually use supercritical CO2 to do some interesting chemistry extractions. I actually use supercritical CO2 to extract oils from an orange peel. So it was pretty interesting. because you don't really use any solvent. So it was really interesting because the CO2 it was like a mixture of a liquid and a gas. So it's pretty interesting to say the least. But usually we use CO2 as a solid. This is dry ice. You see here in this diagram, dry ice. Pretty much we get dry ice at a temperature of, if we're thinking about 1 atm, right? It's about so usually at atmospheric pressure it's like right here. Right here. And then so the temperature is usually like, it should be -78, but usually it's like -40 something. But you see here that it occurs at a low temperature, so we can actually use dry ice for interesting purposes here. But you see the triple point is much lower at a lower temperature than for water. So water has a triple point at 0.01 degrees and 0.006 atm. Well, it's hard to use water in that state. But in this state, we can actually use a CO2 as triple point at 5 atm. But the critical point, if you look at the critical point for water in this diagram here, look, it's 374 degrees Celsius and 218 atm. So that's not very useful just because it requires such a high temperature. Okay, CO2 is more useful here because of its more forgiving conditions in that sense. Okay, so that's all about pretty much phase diagrams I want to cover. It has to do with the phase changes and how we can use each of these phases to kind of use water in different kind of contexts. Okay, all right, so let's move on to solutions. Like dissolves like. So the thing behind this statement is that solutions with similar intermolecular forces can dissolve things better. So non-polar things will dissolve in non-polar things, and then polar things will dissolve other polar things. Okay. So iodine we know is non-polar, right? Because of its structure. And also, what's also non-polar is CCl4, because that's also non-polar. The polar things in this compound, in this mixture, is H2O, the solvent, and the solute KMnO4, which is ionic. Okay, just by going off of this little chart here. So if we were to form a mixture here, we can actually separate these compounds by dissolving it in the appropriate solvent. So iodine will be dissolved in carbon tetrachloride, and potassium permanganate will be very soluble in water. So we can actually separate these things based on their solubilities. All right. So our key terms here are polar molecules dissolve other polar molecules or ionic compounds, while nonpolar molecules dissolve other nonpolar molecules. That's why, when you go off to wash off oil, you use soap. You can't just use water. Soap helps solubilizes the oil molecules and allows it to be washed away by water. So here are the Lewis structures of carbon tetrachloride and water. So although there is charge separation in CCl4, the symmetrical shape causes all the dipoles to cancel out. So there's no net dipole moment. So this is non-polar. Water, because waters are bent and angular, the dipole moments actually don't cancel each other out because the lone pairs makes it unsymmetrical now. So they have now very apparent positive negative poles. So this is an example of a polar molecule. Okay, so water, anything with lone pairs around the central atom, always polar. Okay, so let's keep that in mind. All right, so here's an example of how these interact here. The water molecules can orient with the potassium ion and the permanganate ion to effectively solubilize and make sure that this compound is soluble in water. There's no favorable interaction like this with carbon tetrachloride because it's non-polar, so there's no net dipole moment. But since these ions are charged, it's going to interact with water more favorably. Okay. So I'll talk about why these molecules can dissolve things. It has to do with energetics, but I'll talk about that in a bit. Okay. All right. So let's end this video here, and we'll wrap up the rest of this chapter in the last video. So I'll see everyone then.